an example here, right? Okay, you take this. Okay, let's. I mean, the proof, whatever is done, is the example. It's like I've taken, a simpler case even in the proof. Imagine. Okay, let's start with this eigenvalues of A. All right, and you take one of the eigenvalues and take its corresponding eigenvector. Is the first statement clear? And then I can extend it to a basis. Hello?
Yes, sir. Yes.
So I'm in R3. I'm in like a three-dimensional Euclidean plane, just for understanding. And I have one vector. So if I have to make it a basis, I need two more.
Yes.
You understand what an orthonormal basis is?
Yes, I understand.
If I say Z1 UV is an orthonormal basis, what are the conditions?
So we took the standard basis, other two.
No, it need not be standard basis. You'll have to extend this. The point is,
we can take any basis, orthonormal, but
yeah, if I give you one, if I give you a vector like one with what is the length of that vector in R2? 1.
it's root 2.
Root 2. So if I have to make it normal, I'll have to divide 1 by square root 2.
Yes, sir.
Okay, now what can I add to make it a what other vector can I add to get a basis for R2?
Maybe -1.
Yeah, -1 again is not normal. So
divided by 1 by root 2
yeah,
and -1.
so that's in that spirit you'll have to extend Z1, which is of length 1, assuming it's of length 1. I'll have to add two more vectors u comma v such that I get normal. Yeah, I think there's a typo. Norm of Z1 uv equals 1. This is just a typo. I'm sorry about it. Yeah, I can't edit it here. But whatever is written there, it's an orthonormal basis. Each vector is of length 1, and they are, you mutually, like if you take any pair, they're orthogonal to each other. Is that much clear now?
Yes.
So it's not the standard basis. If I give you a vector, you'll have to make up two more vectors so that the entire set is orthonormal, which is saying that each vector is of size 1 or length 1, and they are orthogonal to each other if I take any pair.
Yeah.
Okay. Now if I take,
can we take the standard basis here? Suppose we have one vector and other, we want to add other two vectors. We can add for suppose for R3. They can be 1 0 0 and 0 1 0.
No, the point is if my first vector is also having the third coordinate 0, then it's a problem. So you have to be careful.
Yes.
You understand?
Yeah.
If my first vector was 1 1 0 scaled 1 by square root 2 times, and if you add 1 0 0 and 0 1 0, then you won't be able to cover the third coordinate.
Right.
You understand what I am trying to say?
So then what should we do to get the other ones, sir?
Yeah, so you need to add the appropriate thing. So the point is,
so can we use the Gram-Schmidt process?
Yeah, you have to do something like Gram-Schmidt. That's the point I'm making. But I just say that if I have 1 1 0, 1 by square root 2, if I add 1 0 0 and 0 1 0, this is not a basis. Can somebody tell me why this is not a basis?
So the first vector is a linear combination of the other two.
Multiplication of
it should be linearly independent.
Multiplication of first and second vector are not 0. They are not
that's one reason. That's correct. What would be a second reason? For basis, what are the two things? Yeah, I should have a linearly independent set of vectors. The second requirement is?
The dimension. Like, there's no information about the third factor that we need.
So I can't get 1 1 1 using these vectors, for example. Whatever linear combination I take, I can't get 1 1 1.
Any vector should be made from these vectors.
Correct, from a linear combination. Okay.
Yeah.
The word is linear combination. Yeah.
Yes.
Okay, so the point is, when you add something, you'll have to add such that you make up basis. You can add any two vectors of any size and use the Gram-Schmidt. We will not see. The point is, it's a proof. So for the proof, I think without loss of generality, we can say that okay, so there is some way we can extend it. There exists some u and v such that I can do this. Understand? If I have one vector in R3, I can easily add two more vectors and get a basis out of it. Is that much clear?
Yes.
All right. Yeah, you'll have to periodically. I mean, I can't see heads nodding, so please say yes or
Yeah,
something.
Yes.
Yeah, because this is the online world. So what I'll do is I'll take all these three vectors and stack them as columns.
Okay, sir.
Okay. And if I apply the matrix A to this. Sorry. Okay. Sorry. Yeah. Yeah. Somebody had a question, is it?
No, sir. Please go on.
Okay. So if I apply A, I'll get lambda 1 in the first column, and the other will be AU and AB. That's simply because Z1 is an eigenvector.
Yes, AZ1 is equal to lambda. That's all.
Maybe I can. How do I minimize this? Okay, go this side. Maybe a way to export this to Notability. Just hang on. Maybe easier if I export this to Notability. Okay. Okay, this bit is because AZ1 equals lambda 1 Z1. So AZ1, the other will be AU and AB. So until here, people made peace. Until here,
Yes, sir.
okay.
Okay.
Now if I do U1 star AU1, what will I get? U1 star is like you take the conjugate transpose, Z1 bar transpose, U bar and all of this, times this. I know AU1 is this. I know AU1 is these columns with lambda 1 Z1 and these two.
Okay.
Got it? So the important thing to achieve is I'll try to highlight something. You look at this matrix, you look at this matrix, these two became 0.
So this is how. So that was my exact doubt from the previous.
Yeah,
how
that's
this matrix came up.
You tell me. What will be this entry? Why is this 0? I think we can make it active learning. Anyone wants to say why this is 0?
So will it be like U conjugate times lambda 1 Z1, and since U and Z1 are orthogonal, so this will be
Yeah, that's the answer. So Kisle, you got the answer? This is
it's because orthogonal.
the reason why we wanted orthonormal basis was because of this reason, because I wanted to start making these zeros. If I take any basis, I won't get this as 0. The reason is like, U and Z1 are orthogonal to each other. U and V also are orthogonal. So, I mean, Z1 and V also are orthogonal. Yeah. So these two entries become 0. Okay. And
Sir, what about star entries? We kept star, na?
No, I want an upper triangular matrix. So I'm going to focus on B and get another 0 here. And so I'm going to make 0 only below the diagonal. So in the end, the theorem wants an upper triangular matrix. I don't care about the star entries. It can be 0, it can be non-zero.
Okay.
You understand the point?
Yeah. This is one more doubt, sir, because it is giving us a diagonal matrix, but wantedly we are taking a upper triangular matrix.
No, it's not giving us a diagonal matrix because these entries need not be 0.
Even in this condition, it is not 0, sir.
Why? I mean, let's take the example. Maybe the example will help you better. You take this. Look at this U1. Look at these entries. Why are these 0? We are not getting 0.
Okay.
Could we also avoid calculating this? We don't really need them.
No, the point is we want this in the sense, if I want to. So the point is here, the claim is like, you're not working with real symmetric matrices. So this Shor's theorem is like, I can use, if I can convert any matrix through some transformation into an upper triangular matrix, then I can use this as, a a tool to prove that, I can diagonalize a real symmetric matrix. Here in this matrix, I am not assuming that, it's real symmetric. You understand?
Yeah, A is any matrix.
Any real matrix, any complex matrix in this case because of U star. So to clarify, I'm not assuming that A is Hermitian. Okay. Yeah.
But then the entries that you have marked with star, then since we don't really need them, even if we don't accurately calculate them, we can manage due
No,
to
that's not the
shortage of
point.
time.
I need the T matrix. I need the T matrix. See,
Okay.
when you diagonalize, let's take this. When I write A, imagine A is real. Real symmetric, just for simplicity. Yeah, is equal to Q lambda Q transpose. What you're saying is you're going to specify this matrix fully, right? Fully specified, right? You're not
Yes.
going to partially specify that. You understand? So
Yes.
in that similar spirit, when I write down that A equals UT U star, then I need the entire T matrix. I need all the entries of T.
Okay.
I want a matrix T is of this form with some numbers here and entirely zeros here. So I want to tell that A equals UT U star with these numbers. So I want to specify, I have to specify, whenever I make a decomposition, I have to specify all the matrices that make up the decomposition. Hope that clarifies. Clear?
Yes.
Yes.
So the point is you just continue. So what you have achieved is you have achieved something for the first column. So just zoom in on B and repeat the procedure. Take this B, take one of its eigenvalue, you'll get a number and 0 and so on. If you keep doing this, you'll get a diagonal matrix. Got it? Is the proof clear, or do you want me to go through all the steps again? The point is, once you achieve this, you take this B matrix. That's your new matrix that you care about. And in this B matrix, again, I can take the, an eigenvalue of this and the corresponding eigenvector, and I can get a matrix like this. Got it? I can make up another unitary matrix P of a smaller dimension because, if this is 3 cross 3, B is 2 cross 2. Is this point clear?
Yes, sir.
So I have a smaller unitary matrix, smaller in the sense it's 2 cross 2. In the 2 cross 2 space, I do something, and then now you need to combine everything. Imagine you combine everything like this, and you get a form like this. So the point is, I got this P matrix, which is unitary, and which is of a smaller size. So I'm going to extend this to a bigger matrix using U2. And I claim that, this U2 is also unitary, and that is shown here. Is that clear? Unfortunately, I'm not getting a response. If people are lost, I can go over this argument again. Hello?
Sir,
Okay, so the point is, I got lambda 1, 0, 0, some numbers, and a matrix B here, right?
yes.
Okay, and now if I just look at this matrix, which is a smaller matrix, this is 3 cross 3, this is 2 cross 2. Okay, and using a unitary matrix, I can do P star BP equals this. Is this much clear?
Yes.
Okay. Now the point is, this P star is a smaller matrix. I want to work with the A, that is a bigger matrix, 3 cross 3. I have U1 star A U1 equals this. Do you see these two bits? Now the point is, this is a smaller matrix, so I want to scale it up to a 3 cross 3 matrix, and that is done in this shaded bit. And that's what is U2 doing. I'm scaling it up to a 3 cross 3 matrix.
So for what these steps are what you have did, sir? This is not clear. You have
No,
just added.
the point is, okay, if you take U2 and U1, and if I apply if I look at this product, this entire product will be a upper triangle matrix. Got it?
Okay, sir.
So I have U2 star, U1 star, A, U1, U2 is a upper triangular matrix. Got it?
Yes, sir.
So I can write it as U1, U2 star A, U1, U2 equals upper triangular matrix. And that's exactly what you wanted. You take things on the other side, you will get it in the other form. If I call this some U, let U equals U1, U2, then what I have is U star AU equals upper triangular matrix, which is exactly what we wanted. Just we are written it in the other form. Yeah. This is equivalent to writing U star AU equals upper triangle. Got it?
Yes, sir.
Why is this equivalent? At least that part should be easy to answer. How do I get from here to here?
So we left multiply both sides with U star and right
Yes.
multiply with U. And
Yeah. And you'll get it. Okay. I think everyone is at peace with that. Yeah. So the point is that's exactly what I achieved. The point I want to make is when I look at a smaller matrix and make up a unitary matrix for that, smaller matrix B, eventually I'll have to make up a unitary matrix for working with A. So if you look at this, I'm going to multiply with U1 star and then U2 star. So I don't have a U2. So for U2, I'm going to use a smaller unitary matrix and put 1, 0, 0, 0. Because this zeros, I mean, this part alone I've already covered. I don't really want any more transformation in this part. In this part of the matrix, I don't want any transformation. I want to make the other matrix upper triangular. That's the reason why I put a P here. Is that intuitively clear?
yes, sir.
See, the point is, the moment I get U1 star A U1 equals this, I'm happy with this column and this row. I don't have to make any more changes to that column and that row. Is that clear?
Yes, sir.
So so when I make up a bigger U2 here, I'll retain these as is. And I'll work with the smaller thing so that that smaller matrix becomes like this. And if you have more than 3 dimensions, you continue this logic for, until whatever the dimension is. And you keep repeating this, you'll get the upper triangular matrix. You'll keep working with, imagine you have an n cross n matrix. Then you'll make the first column, of this type, which is like some number, and rest of them are zeros. You'll take a n minus 1 cross n minus 1, and that again you'll turn it into a matrix like this. It won't be 2 cross 2, but it will be n minus 1 cross n minus 1, and so on. You'll have to repeat this so that finally you will get a unitary matrix. Is that logic clear about Schur's theorem? The interesting thing is we did the same thing, in this example. If you see, we followed the same steps as in the proof. So if you understand the proof, you get the example, or the other way. It's the same steps. You take this, eigenvalues, the corresponding eigenvectors. I mean, you are asking this question, right? So I take Z1, I add E1, E2 and make it orthonormal. Yeah. So that's already there in the notes. I didn't even know this. Yeah. But I'm just saying that, you'll have to look at the first eigenvector before deciding what 2 vectors you're going to add. Yeah. So you should not end up in a situation where, one of the eigenvectors has a third coordinate 0, and then you add these two basis elements and hope for an overall basis. That won't happen. So you just have to be careful about it. Yeah. Okay. Okay, folks, does this cover Schur's theorem? Any questions?
So to find the upper triangular matrix, we have to follow this approach only, like iteratively find the unitary matrix.
Yeah, I don't think there's, at least I'm not aware of any other way. I mean, there's no easy way, right? I mean, you'll have to go through these steps.
Yeah, I'm just confirming, like for diagonalization, we just find the eigenvalues and we can just...
Correct, but this is a matrix that's not symmetric. Look at this.
Yeah. Yeah, that is why I was asking. So this is the only way we can upper triangulize it.
That I can't answer. In a sense, I know this is one reasonable way to do it. If there is another way to do it, honestly, maybe there is some other way. At least it's not apparent to me. Yeah. Let me put it like this. If it is real symmetric matrix, you don't have to work this hard. You know how to solve.
In that case, we just diagonalize it.
Yeah, you just diagonalize. The diagonal matrix is trivially upper triangular. Yeah.
Yeah.
So in the case where you'll have to do maximum work is you have a real matrix which is not symmetric. Then you'll have to go through all these steps.
Got it.
Yeah, the point is this is like a tool. This is like one of the steps for like once you have this, if you follow the spectral theorem proof, once you have this spectral theorem, which is like I can diagonalize it, I can do unitary diagonalization of a matrix, of a Hermitian matrix, follows in like 2 or 3 lines.
Yes.
Once you have this, yeah. Once you have this, so this can be seen as like a building block for the final theorem, which is spectral theorem. But this building block is of independent interest. Given a matrix, I can make it upper triangular. Like if you have an upper triangular matrix, you can solve the linear system of equations easily. Is that clear?
Yes, just
Right?
like sir, echelon form, like we did it.
Yeah. So if somebody has given you a matrix in upper triangular form, I mean, just so simple. Yeah. So there are benefits to having a matrix in an upper triangular form. Yeah. Anyway, so what's the next thing? Shall I just try some geometric ideas?
Yes, sir, that will be fine.
Okay, let's see. Just some simple stuff. Let's start with some simple stuff. So I hope everybody knows what orthogonal vectors are. These two are orthogonal because the transpose in the real case. Yeah. Now the question is, are these x and y orthogonal? What is x transpose y? X transpose y equals? Hello? Are people able to see my screen?
Yes, sir. 0.
Yeah, yes, sir. 0.
So are they orthogonal?
Yes.
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 Yes. So you fell for it. It's complex.
Oh.
First one is.
X bar transpose.
Yeah, you need to do x bar transpose y equals 0
Right.
for complex case.
Sir, I was thinking like it's 0, not dot.
Yeah. Anyway, just as an appetizer, I had to start somewhere, so wrote something. I think orthogonality is clear. Now let's look at orthogonal complements. So if I look at this x is 1, 1. Is this clear? This is the 2D plane. 1, 1. So if I have, what is the span of this x? Is it a line or a plane? I mean, somebody has to talk. I want to
It's
this
a line. It's a line.
Line, sir.
Lines.
This is a line.
Yeah.
So if I want to look at it orthogonal complement, where will that be?
Down, sir.
Y equal to minus.
Yeah, like this. Conjugate.
Yeah. So can somebody tell me the coordinates?
Minus 1.
1 comma minus.
1 comma minus 1.
So you can take this line. I think so. The orthogonal complement is this line. Okay. Yeah. Just that. Now let's look at R3. If I have S is span of 2 vectors, my favorite vectors. Give me 2 vectors, orthogonal vectors. Span of 2 vectors.
1, 0, 0, 1.
1, 0, 0, 1. What is the orthogonal complement? Orthogonal complement.
So shouldn't the vector be 1, 0, 0, 0, 1, 0?
Thanks.
0.
Now,
The complement is 0, 0, 1.
yeah, this is the span of. So this is a plane, and its orthogonal complement is a. I mean, if I take 2
It will be
vectors,
also plane.
is it a plane?
It's a line.
It's a line.
Line, sir.
It's a line. Is that clear? So you're in 3D space. So if you look at the span of two independent vectors, that will make up a plane. And if I
Yes.
look at its complement, its dimension is 3 minus the dimension of this, which is 1. So which is a line. Got it?
Yes.
Okay. Anyway, we'll go further. So I just wanted people to recall. So orthogonal matrix, everybody knows. It has orthonormal columns, all of this. What is Qx equals? What is this property of an orthogonal matrix? Q of x equals what? Does
The
it
X
change the
itself,
size or does it keep the size same?
it keeps
Keep
the
the
size
size
same.
Okay, so this. All right.
just rotate.
Yeah, so I would add, if I want to do this for unitary, what would be the change? Say u. Here, what would be change?
U inverse
U
is U star.
star is equal to
Yeah. Okay. And so on. I mean, orthonormal columns, here, orthonormal columns will be the same, except that, you'll have to take conjugate transpose. Yeah, use conjugate transpose. Use conjugate transpose to define orthogonality, and they won't change the thing. So what should I write? Yeah, I need water. Sorry. Yeah. Yeah, here also it's the same thing. Sorry, I'm back. Shh. Okay. All right. So the next thing I want to do is, so the important thing I want you to note from a geometric viewpoint is, if x has a certain length, and if I apply q or a u, it won't change the size. The size will remain. So what could happen is it could be rotated, but it won't change the size. Is that point clear? That's the implication, geometric implication of this property 3. Yes?
Okay.
Okay. Now I just want to,
So both the matrices will preserve the length.
sorry, what?
I mean, both the matrices will preserve the length.
Yes,
of
both
the-
will, both will. I mean, unitary is just a generalization of orthogonal matrices to the complex case. So instead of doing normal transpose, you add conjugate transpose, and you use that conjugate transpose to define your norm. And yeah,
Okay, sir.
so if you use conjugate transpose to define your norm, then all of it carries through. The idea is they don't change the size. Yeah.
Okay, sir.
So they can rotate. So if I want to work this out, let's go through some simple thing. Imagine I have a vector x, and I want to rotate it and rotate it anti-clockwise by theta. Got it? So I want to make up a matrix. I want to write y equals some p times x, and this rotates anti-clockwise by theta. Is this problem statement clear?
Yes, sir.
So how do we approach this? I'll just show you some simple ideas. Imagine this x has length a. Clear? So when I rotate, the length won't change. Are people okay with this claim?
Yes, sir.
Okay, I'm rotating it and I'm not stretching the vector. I'm just, rotating it. Now, using just, simple trigonometry, what would be y? Are people okay with this? y1, if I write y as y1 comma y2, then it's making an angle theta plus phi, theta plus phi. So its x coordinate is going to be, the length of y is a, so a times cos, and y coordinate is a times sin.
Yes, yes.
Is that clear?
Components.
Yes, sir.
So y1 and y2 are clear. Now, does everyone remember cos a plus b formula?
Yeah, cos theta,
Yes,
cos
sir.
phi minus.
Opposite by hypotenuse and sine is opposite by hypotenuse.
No, I mean cos of a plus b formula, which somebody was actually telling. So this one.
Okay.
This is cos of something plus something, and that turns out to be this. Until here, I hope there are no doubts.
No doubt, sir.
Yeah, no doubts. Thanks.
Hmm.
Any doubts about this side box?
No doubt.
Okay. See, the point is, I don't want to keep phi. So finally, this matrix should entirely depend on theta. I don't want to bring in the phi. You understand? I should take the x coordinates and do something so that I get the y coordinates. You understand? I don't want to work out the phi, so I'm going to try and get rid of the phi.
We can make it x1 cos theta minus x2
No.
sin.
You're taking
No,
inverse.
I'm just saying I'm going to use this side box for that.
Okay.
Yeah. So see, the point is this: a is also the length of y.
Yes.
So I just want to get rid of phi, which is what I have done here. Look at this. So if I use cos phi equals x1 by a, the a goes off. Same thing for sin phi, sin phi.
Okay, got it.
So you got this. So in this equation, I don't have any more of this phi. And I have arrived at the matrix. See, this is my matrix.
This is the rotation matrix what was taught in last one match 2 also, sir.
Oh, it was taught. Wow, okay. Anyway, it's okay to revise
Yes,
things.
this is the standard rotation matrix for 2 dimensions.
Okay, so then was the generalization to 3 dimensions taught?
No, so it was just given like just extended.
Yes, it was not taught like this. This was the proof, and we were not aware of.
No, the proof is elementary, right? Now that you
Yeah,
can,
it's elementary.
yeah, it's elementary, but it's good to see it once. I'm not sure at what level, what knowledge you have. So I'm just going to
Yes,
put some things. Some things will be very easy. Some things may be too
Yes,
difficult. So we'll just suffer. Yeah. Yeah. So, okay, I called it Q. So I'll make this Q. There's a reason why I call this Q. Why am I calling this a Q? Why is it orthogonal? What's the length?
Length
What's
is
the length?
1.
1. You understand? And you take the dot product. If you look at these columns, are they orthogonal to each other?
right, sir. Yes, sir.
sir.
Okay. So I
And
hope.
the length is 1.
Yeah. So this is an orthogonal matrix. So I'll just write Q is orthogonal matrix. Got it? So far,
Got it.
now I'll show how to do this for R3, where only one of the rotations I'll handle. Okay, and there is some geometry here, you'll have to pay attention. So imagine, so this is my X, Y, and Z axis. Do people see this? And I have an X, which is X1, X2, X3. Does everyone see this X1, X2, X3?
Yes.
And I want to rotate it around the Z axis and make it Y1, Y2, Y3. Understand? Forget the other parts of the picture. I have a vector which is X here, and I want to rotate it so that I come to Y.
Is it clockwise, anti-clockwise will not be a problem?
Yeah, this side.
It's anti-clockwise.
Clockwise only. The point I want to make first is, the first thing to notice, because I'm rotating around the Z axis, this coordinate won't change.
Yes, sir.
Got it? I hope geometrically you convince yourself. Yeah. It's going to be at the same height.
Yes.
The height won't change. So along the Z axis, the height won't change. So once you're convinced, so what are the things to figure? I have to figure Y1 and Y2 as a function of theta and these X1 and X2. Clear?
Yes, sir.
That's the problem. Now, if z does not change, the interpretation I want to make is I can project this onto the xy plane, which is like making x3 0 and y3 0. Hello?
Yes, sir. Yes, sir.
So if I take x1, x2 0 and rotate it counterclockwise by theta, I'll get y1, y2 0. And it will be the same y1, y2 even if I throw in a x3 and y3. X3 and same thing, x3 equals y3. So if I throw in an additional z coordinate, the x1 and x2, that rotation logic will still hold. So I can simplify this to the 2D case. Do you understand?
Yes, sir.
So the point I'm trying to make is I just need to figure y1 and y2. So I can pretend as if there is no third coordinate and just do the rotation. Now if I'm given x1 and x2 and if I have to rotate counterclockwise by theta, then I already know there is a matrix here. Got it? Now how do I extend this to a 3 cross 3 matrix for rotation? Are people able to follow the train of argument so far?
yes, sir.
Make the last row and last column 0.
Yeah, so the point is Z, I don't know if you said the same thing, Z will remain unchanged.
So it's like the shoes theorem we did right now, right?
It's not about Schur's theorem. The point is what happens is I'm rotating. My requirement is to rotate around the Z axis. Not any rotation, but rotation around the Z axis, which just means that x3 is going to remain the same. So the third coordinate is going to remain the same. So I need to write x1, x2, x3. So the third coordinate is going to remain the same. And for x1, x2, I can apply this smaller matrix to rotate and I'll get y1, y2. This is the same matrix that was worked out here. And the rationale or the justification for this is that, I can take these vectors, ignore the last bit and make them, push them onto the xy plane and do the same rotation. And going from x1 and x2 to y1 comma y2 will, it will follow the same, argument. You understand? It's equivalent. If I have to rotate here by theta, it's the same rotation I'll have to do here also. The angles won't change. Yeah, I think people have to tell me whether they understood. Otherwise, I'll try to tell this again. Yeah.
Got it.
Yeah? Understood? Okay, great. So the next.
Third coordinate we wrote one, that I didn't understand.
So the point is, see, when I rotate x3 equals y3, right? Or let me write it the other way. I want y, I have x. The third coordinate is unchanged, right? So I'm given x1, x2, x3. And when I go to y1, y2, y3, if I multiply by this, if I have a 1 here, then y3 is going to be equal to x3. Clear?
Yeah, keeping that same height. We are taking the point at same.
Yeah, the point is I'm rotating around the z. So the height will remain the same. That's the construction.
Yes.
Yeah.
But so this is one special case, no? It is not a generalized case.
Yeah, this is one special case. I think you can write down these matrices for, rotation around y-axis and rotation around x-axis also. Yeah. Okay, so I just want to add one thing about projection, which I have not written. Just something about projection. Just a useful interpretation in case you have not gone through this. Imagine I want to project. Let me write this. This you must have seen many times. It may come in tomorrow's quiz also. Project, say V, onto the line through X. All right, you have some X here. You have some V here. Want to do projection, orthogonal projection. That's orthogonal, okay. And then I will get PV. And now what is P? This is a quiz question.
Projection matrix.
Correct. I want the formula.
XX transpose by X transpose.
That's correct. Okay. Suppose norm X equals 1. Then P is XX transpose. All right. If X is a unit vector
Yes, sir.
or unit length vector, whichever you like. Yeah. Now, if I look at PV, this is in this case, in this if case, yeah, X into X transpose V. And that I can write as, see, this is a scalar. So I can write it as X transpose V into X. Okay? Yeah?
Yes, sir.
Now what is the length of PV?
X transpose V mod and like the length of X.
But what is the length of X?
1. So it is the X.
Okay? So the point I want to make is when you project this length is so when I do dot product, so X transpose V is the length of the orthogonal projection of V onto X. Clear?
Yes, sir.
Yeah, so that's just saying that, you can visualize, you can look at this dot product as the length of an orthogonal projection.
Sir, I have a doubt in that second line where X into X transpose. We taken X into right side, right?
Yeah, see this X transpose V, is it a number?
Yeah, it's a number.
So I can write that on this side, right?
Right. Understood.
What if the norm of x was not 1?
Sorry, what?
What if the norm of x was not 1? Then,
Yeah, then
what is the length of PV?
No, the point we are trying to make is I want to understand what X transpose V means. So I'm just saying that I can understand X transpose V as the length of orthogonal projection of any vector of vector V onto the line through X if X is a unit length vector.
Okay.
So if you want to understand what X transpose V means, you can interpret it as a certain length, and that length is the length of the orthogonal projection. Yeah. So this if is to just understand X transpose V, which is an inner product.
Okay.
Yeah.
Thank you.
Yeah. So I mean, when you look at inner product, you will see, okay, there's an angle and all of that, right? But this interpretation says that you can see it as the length of a certain vector after orthogonal projection. Yeah. Okay. I think the next is positive definite matrices, and I just okay, just some simple things to get started. Let's see. If I have restricted to real symmetric case in this course, so I'm going to define positive definiteness only for real symmetric matrices, and this is the condition. Whatever I've highlighted, this is just a refresher, which is like saying that all the eigenvalues are strictly positive. Is positive definiteness recall okay?
Yes, sir. You have brought, sir, 4 conditions, if I remember.
Yeah, I'll just work with these two for geometry.
So any of the condition will be sufficient for
Positive definiteness.
Yes.
You can start here and come here. You can start here and come here.
Yeah. Okay.
Yeah. These are equivalent, so you can replace this by an equivalent. It goes both ways. Yeah. You can use any one to define the other. I mean, you can say that a matrix A, which is D cross D, is real symmetric, is positive definite if all of its eigenvalues are strictly positive, and you will get this. Or you can define it like this, and you will get this. I think the proof was done in the notes. I may have done this. may have done the proof. I don't fully recall. It's been a while. Yeah. Okay, so the question now is, I mean, geometry is coming soon. Just some appetizer. Imagine I want to solve Ax equals B. The least squares approach is to solve this. Do you remember this famous equation?
Yes, sir.
Yeah, this is a famous equation. Yeah, it does not have a name, but it's a famous equation. Now, if I look at A transpose A, it's symmetric, right?
Yes, sir.
Is everyone okay?
Yes,
Is
sir.
it positive definite? Let's hide this. Is A transpose A positive definite?
May or may not be some, not always.
Not always. Okay, but can you just look at this product? If I have this, I get until this point. You look at this, whatever I have written. Is this equation clear? The highlighted equation?
Yes, I have used previous equation like A transpose A square.
No, I am just using, this has nothing to do with least squares so far. I'm just working with A transpose A. There's a connection to least squares which is coming soon. The point I want to make is, if I have a positive definite matrix, is it invertible?
Yes, sir.
Yes,
It's
sir.
invertible.
Yes, sir.
Because determinant is not equal.
Yeah, so then I can take this A transpose A on this side and write an inverse. And in that case, X hat will be unique. Is that logic clear?
Yes, sir.
I'll just write it here. If A transpose A is positive definite, implies A transpose A inverse exists, implies X hat equals A transpose A, what is it, inverse A transpose B, or X hat is unique. There's only one solution. Clear? So one way to
Yes.
guarantee that is if A has linearly independent columns. If A has linearly independent columns, then this norm Ax is 0 only for x equals 0. In all the other cases, it's greater than 0. And hence A transpose A is positive definite. Got it? I have not written that logic here, but I want people to ask me a question so that I can write.
Oh, sir, can you repeat the last line?
Yeah, I can repeat. If A transpose A is positive, then okay. So if A has linearly independent columns, let me erase this. If A has linearly independent columns, then X transpose A X is equal to norm A X square greater than 0 for all x not equal to 0. Is this condition clear now? Whatever I have written here, this bit, or A transpose A is positive definite. If A has linearly independent columns, then what is the rank of A?
Full rank.
Full rank. So what is the rank of A transpose A? Full rank. That means it's invertible. That just means that, norm Ax can't be 0 for a, there's nothing in the null space, so that I'll get this as 0. You understand? Ax won't be 0 for any x other than 0. And that's the reason why I'll get this as greater than 0. I've said all of this orally. I just can't write the whole thing. I hope I can repeat this orally again if something is not clear.
Oh, yes, sir, understood.
Sir, it's clear.
Understood. Clear, sir.
Clear?
Yes,
I'm
sir.
saying A transpose A is positive definite. If I have linearly independent columns, then I get A transpose A is positive definite. A side implication is that the least square solution is unique. Is that clear? Can we move on to the next thing?
Yes, yes.
Yes, sir.
Yeah, if you people want a 1 minute break, I can, because I've been dumping a lot of geometry. It's only going to get a lot more involved after this. So if you want to take a 1 or 2 minutes breather, it's fine.
Okay, okay, fine.
Yeah, let's take 2 minutes, 2 or 3 minutes break. Now it's 3:05. We'll resume. I'll just step out and be right back. Okay, I'm back. Let me briefly. Where is my meeting? Is it here? Yeah, who's the TA? Ram, is it? Ram, or who is it? Is there a TA here?
Yes, sir.
I can't find you in the list.
Vishal.
Okay, Vishal. Okay, Vishal. This whatever I'm writing in a note, is there some way of sharing it with the students?
Yeah, yes, sir. You can share that.
So if I just email it to you after the meeting, you can handle it, right?
Yes, yes, sure, sir. I'll upload it on the portal or maybe on the Discord also.
No, I think this is very rough calculation. It's not like something that should be out for public consumption, because I'm just giving some ideas, right? Not writing out the entire argument. But if there's a way that students can check it out, it's fine. But it should not be like some lecture note or something, because I'm not written out all the arguments. You understand?
Yes, sir. So we'll share it on the Discords.
Yeah. So, all right. So let me get back. So this is recorded, is it? There is share. Changing it. Okay. All right. So we'll continue the serious discussion because we are on record. All right. So now the geometric interpretation of this business of positive definiteness. So until now, if you have any questions about any interpretation, I'll be happy to take questions. Anything about orthogonality or projections or this, whatever I have written so far. which is about 4 pages. Still about 5 or 6. Okay, 4 pages. Any doubts? No doubts?
Clear, sir.
Okay, great. Yeah. So you're a good audience. Thanks. So let's try to understand this positive definiteness using some geometry. So I'll write some line here. Okay, so what I'm looking at is this. I want to understand where is the geometry coming in. So let's start very simple. This x transpose x equals 1. If I take a simple 2D case, that's the equation of a circle. x1 square plus x2 square equals 1. That's the equation of a unit circle. Now if I extend this to d dimensions, I will get the equation of a unit sphere. Yeah. Following this?
Yes, sir.
What is the center of the sphere?
0, 0.
Yeah. Why?
Radius 1.
Yeah, that's something you need to think about. Why is it not something other than the origin? I think way to argue is like, both x and minus x satisfy this equation, but I'll leave it. Yeah. My point is not about the center, it's something else. Now, instead of this, if I scale all of them by, 4, the coefficients, then I get a smaller sphere. Clear? Because this is equal to 1 by 4. The radius becomes smaller.
Yes, sir.
All right. Again, centered at origin, that's fine. Now, if I take...
I'm sorry to interrupt. This is 4 times x transpose x is also 1.
No, if this happens, I'm just saying that, if I have x transpose x equals 1, I get the equation of a unit sphere.
Right.
Right? But if I have 4 times x transpose x equals 1, then this 4 times x transpose x is like 4x1 square plus all of that. Yeah? That just means that I get an equation of a sphere, but it's not unit sphere, but a sphere that is smaller than the unit sphere.
Okay.
Yeah?
Yes.
Yeah. So if, let's put a if. Yeah? Right. Now the point is, instead of putting 4 for uniform coordinates for all, I can add different coordinates. Way to do that would be to take a matrix, diagonal matrix, and have different entries, unequal entries. So if I write x transpose AX with this A, can somebody tell me the equation in terms of x1 and x2?
4x1 square plus x2 square.
Yeah, 4x1 square plus x2 square. Now this is no longer a circle. Is that clear? It becomes the equation of an ellipse. You understand? So the point is, the moment I have unequal entries, I no longer I'm stretching the coordinates equally in all directions. I'm doing variable stretching. So I will get an ellipse. Now, just some basic high school mathematics. What is x? Whatever I have marked there in 2D. What are the coordinates of x?
Half comma 0.
1 0 and 0 1.
1 0. If I put 1 0, I'll get 4, right?
No, it's 1 by 2. It's 1 by 2,
Yeah,
comma
1 by 2.
0,
Yeah, 1 by 2
comma 0 or 1 comma 0.
1 comma 0.
0 comma 1.
0 comma 1.
0 comma 1.
Thanks. Yeah. Yeah, that's okay. So if I have to look at this is the major axis and this is the minor axis. I can stretch this further. I mean, the same logic works. I will get an equation like this, but it's no longer an ellipse because I'm in, three-dimensional space, becomes what is called as an ellipsoid. This is just a generalization of an ellipse. You see this equation that I'll try to put it in red box. This equation that I'm highlighting is the equation of a something that's like a generalization of an ellipse. It's called an ellipsoid. So the point I'm trying to make is, when I write X transpose X, there is an identity matrix sitting here. So if X transpose X with an identity matrix sitting here leads to an equation of a circle or a sphere. But the moment it is not an identity matrix, then it becomes an ellipse. So this equation that I'm looking at, X transpose Ax equals 1, leads to different geometric interpretation. It's either a sphere or an ellipsoid. Got it? With diagonal matrices. So far, are people with me?
Yes, sir.
Okay, so now the question is, what if I take a matrix which has off-diagonal entries? So the problem is, what happens then? Why can't I just say that it's still the equation of an ellipse or an ellipsoid? What extra bits I will get if I have off-diagonal? Sorry?
You will get terms like x1, x2, x2,
Correct. You will
x3.
get the cross terms. You will get the cross terms. So in that case, can I still figure out? Can I still do some geometric interpretation? That's the question. All right. So I will take this matrix 5, 4, 4, 5. What are its eigenvalues? Its eigenvalues are 1 and 9. Okay. It's just elementary. So the question now is this a positive definite matrix?
Yes, sir.
Yes, sir.
Yeah, trivially. Thanks. Now, what is X transpose Ax? It's this equation. I'll give you some time so that you do this product. But if you want a faster way to compute this goes with x1 square, this goes with x2 square, and this plus this goes with x1 and x2. And the same logic you can extend to d dimensions. You just have to collect the right cross terms. Yeah. Okay. Is X transpose Ax clear to everyone?
Yes, sir.
Now this is
Yes,
not
sir.
the equation of an ellipse. If I write X transpose Ax equals 1, I'm still far from an ellipse because of this. So I need to do some manipulation. Clear? So I'll do that manipulation, and for that manipulation, I'm going to use the eigenvectors of this matrix. So the eigenvectors are easy to calculate. Thankfully, it's a very simple matrix. So if you take, it's 5, 4, 4, 5. If I subtract 1, I get 4, 4, 4, 4. And for this, I think you don't have to work too hard. Minus 1, 1 or 1 comma minus 1, both of them are okay. And I want what do you call? I want a vector of length 1. So I'm going to normalize. This is my first eigenvector. All right, you people should be able to understand this well enough.
Yes, sir.
Because you have a quiz tomorrow. Along similar lines, you'll get another eigenvector. So I'll just let you stare at this for 10 seconds to convince yourself that you're looking at the right eigenvalues and eigenvectors. So the important thing is, when I try to get to the geometry of this, please follow the argument. If you miss anything, you can ask me. Because I'm going to still make up an ellipsoid using this eigenvectors and the eigenvalues. And the important thing is, if you look at the ellipsoid that, or the ellipse that I got here, it was aligned to the x and y axis. The axis of the ellipse the axes were aligned to the XY axis. Whereas if you have off-diagonal entries, that may not be the case, but the alignment will happen to the eigenvectors. You'll get an ellipse with axis aligned to V1 and V2. You don't have to believe me. I'm going to show this. I'm just saying this so that next I'll make up an ellipse with the axis aligned to the eigenvectors. So I'm stating something and I'm going to show that. So is this fact clear? So it's like saying that I'm going to rotate the ellipse. So instead of having an ellipse like this, I'll have a rotated ellipse. Got it?
Yes, sir.
Yeah. So how do I make that up? How do I find the major and minor axis? I'm going to show you some steps which will generalize to d dimensions. And here is where our usual diagonalization or spectral theorem comes into picture. So I can write A like this. See, remember the eigen vectors are these. So I stack them as columns. I stack them as columns here. And then take its transpose here and throw in the eigenvalues in the diagonal matrix below. I mean in the middle. So I want to ask, is this clear?
Yes, sir.
Yeah, so diagonalization I hope is clear. So I got a orthogonal matrix Q and its transpose here. And I have to throw the eigenvectors as columns here. Now look at this product. What am I trying to do? I am going to simplify this X transpose AX using this form. I'm going to use this diagonal form. I'm going to use this diagonal form to simplify X transpose X. All right. So X transpose X, A is Q lambda Q transpose. And so I can write this like this. So this is something that we will do many times. And if I denote Y equals Q transpose X, then I get an equation like this.
And Y is just the rotated version of X.
Yeah, Y is just the rotated version of X. Now
Because
you know why it is the rotated version, because
Q is orthogonal.
Q is orthogonal. I was just trying to show. That's the reason why there is some method in this random geometric interpretation that I'm trying to show. That cos theta, sin theta, all that business I did so that people realize that I can rotate using orthogonal matrices. But what is this equation?
Equation of ellipsoid.
Yeah, it's an ellipse. Anyway, it's 2D, so it's ellipse.
Okay.
Yeah. Okay, so in these I will get, and now I can write this out explicitly. I've just done some hard work for you folks. Just follow this. Q transpose X is this. And if I write down this whole thing, I get the equation finally like this. I think this entire thing going from here to here is simple algebra. So if this equation 1 is not clear, I'll let you stare at this equation. If you have any questions, ask me. I may have made some mistakes. Just check if there are any typos or errors. If I say X transpose AX equals 1 using equation 1, then I get the equation of an ellipse. Just probably written here. So yeah, I want you people to get up to equation 2. If you get there, you are very close. I mean, you're just one step away from understanding the geometry involving positive definite matrices. Just one more step. So if equation 2 is clear, if how we got to equation 2, stuff like that is clear, then we are nearly done. We just have to figure the axis of this ellipse and we are done. Any questions about this business up to equation 2? Is it all clear? People awake? I understand it's a time when I'm fighting
Yes,
my
sir.
sleep and your sleep. Yeah. Hello?
Yes, sir, it's clear, sir. Please go ahead.
Okay. So if you are all okay up to equation 2, I'm just going to state that continue from there.
Yes, sir, yes.
All right. So if you look at equation 2, I mean, if I want to make, if I want to choose x1 and x2 such that only the first term is 1, then that will be this. Got it? This is the eigenvector corresponding to the eigenvalue. This is the eigenvector for lambda equals 1. And this is 1 by 3 times eigenvector. I mean, this is also an eigenvector, but it's just scaled. How do I write this? Eigenvector for, okay, I'll write it. Nine, is it? You got 9 only, no? Yeah, 9 only. Correct. Okay, but the important thing to notice is there is a scaling 1 by 3. Yeah. Note the 1 by 3 scaling. So the final ellipse is here. This is one of the eigenvectors, this is the other, and this is scaled. This becomes minor because of the scaling 1 by 3. So the principal axis for a ellipse equation here corresponds to the smallest eigenvalue. So if I take the smallest eigenvalue, that will decide the major axis. And that's because if you go here, if you look at this equation, you have lambda 1 here, which is like y1 square divided by 1 by lambda 1 plus y2 square divided by 1 by lambda 2. So if lambda 1 is the smallest, then that becomes the principal axis. So I want you to parse that statement. Yeah. And the same logic works for ellipsoids also. Like, you can go on the, the first principal axis is this, the second principal axis will correspond to the second smallest eigenvalue and so on. And the largest eigenvalue will be the minor, will be the minor axis. Clear? This is where, you understand what's happening. Yeah. Any questions about this?
Sir, around z axis, when you rotate this, then that value it becomes 1 by 3 root 2, right?
Sorry, what?
When
So the point is, this becomes smaller, 1 by 3. You have to do this 1 by 3 because there's a 9 multiplying here. You understand? This 1 by 3 came here because 1 by 3 square has to cut the 9 and so that I get the 1 eventually. So you get the eigenvectors, whatever you had, normalized eigenvectors. But this scaling is essential because this has a 1 here. So there is a hidden 1 here. There's a 1 times this and 9 times this. So the smallest eigenvalue, I didn't have to scale anything. So the major axis is B.
Okay.
Got it?
Yes, sir.
Yeah. So the major axis will correspond to the smallest eigenvalue. That's the point you have to remember. Yeah. And that's and the other thing is, this ellipse has axis that's not aligned to the xy axis. It's rotated. And it's aligned to the eigenvectors. Okay, the axis of the ellipse gets decided by the eigenvector. So the point I'm trying to make is, if you go to the easier example here, the axis of this ellipse is aligned to the x and y axis. That's simply because there are no off diagonal terms, no cross terms. Whereas if there are cross terms or the off diagonal terms, then what will happen is it will amount to having an ellipse where you add a rotation, and that's coming from the Q transpose. Okay. This business about Q transpose. So if you want to look at it, what is Y? What is Y? Y is Q transpose X, right? So you have the ellipse equation in this, Y equals Q transpose X. If you look at this. Okay. I hope this much of the geometry is clear. There's still something left. If you have the heart for it, I'm going to give you the geometry for SVD also, using logic similar to this. So if you don't understand this, you can try understanding SVD, and eventually you'll get both. If you get this, you get that, or you get neither. Yeah. Any questions? I mean, if you want me to summarize again, so the point I'm trying to make is, if you're looking at X transpose AX with a matrix A whose diagonal entries are all equal, then I get to a sphere. Whereas the moment the diagonal entries are unequal, I get an ellipse or ellipsoid with axis aligned. And if you have off diagonal entries, then the axis won't be aligned to the X and Y. Yeah. This is X, this is Y. Yeah. I should not use X and Y because Y is some other thing. Okay, I'll just leave it at this. Because Y is equal to Q transpose X, so I don't want people to get confused. Yeah. Any doubts about this geometry so far? No? Can move on to SVD?
Yes, sir.
Yeah.
So angle between the new major and minor axis will remain 90.
Yeah, it has to.
Because we are multiplying by the same orthogonal.
No, these are orthonormal eigenvectors, right?
Yeah, okay.
No, these eigenvectors, okay. Yeah, these are eigenvectors which are orthonormal.
Yeah.
Yeah. It's just, instead of the X and Y axis, you have the eigenvectors from an orthonormal set. So it's like, it amounts to something like, I can try doing something. It amounts to something like doing this. Got it? Where the axis will no longer be aligned. Understand? Now I'll do undo. So the moment you have off diagonal entries, it amounts to rotating the ellipse. And the new axis will get decided by the eigenvectors, and the major axis is decided by the smallest eigenvalue. That's the point I want you people to take away. With all this calculation, the important thing to take away is this major axis corresponds to the lambda equals 1.
Sir, there's a question in the chat box that how does it fit into the PCA?
PCA I can't do today, but I'll do SVD. For me to do geometry of PCA, it will take 1 hour. I thought I'll cover basic geometry. I mean, you have to understand ellipsoids before getting to that. So if you understand SVD's geometry, which I'll cover next, then you can attack PCA. Because PCA is like, you do SVD and get something out of it. Okay. That's a very, very vague answer, but you have to understand the geometry behind SVD, which can be used to achieve PCA. So you have to understand what SVD does. Got it? So right now I'm just in the space of positive definite matrices. The next stop is singular value decomposition. Just a brief recall, like the shortest summary of SVD is I can write any matrix as like this, where I'll get the singular values in a diagonal matrix and zeros elsewhere, and I'll get two orthogonal matrices of different dimension. And these singular values are the square root of the eigenvalues of A transpose A. Okay, now to the geometric interpretation. For geometric interpretation, I'll take a square matrix and I'll also assume it's invertible. You can generalize it later. Yeah, I think you can generalize it. You can try doing some reading to generalize it to the case where it's not the case, where these assumptions are not met. So for the geometric interpretation, I'm looking at a square matrix. This is a square matrix. Square matrix that is invertible. And these are the singular values. Is the notation okay? Is everyone on the same page? Are people with me so far for SVD? All right. So the way to understand SVD is this. We have been working with unit square and unit sphere. So look at the unit sphere. What is the unit sphere? This is the 2 norm. This is the set of all vectors which has length 1 in d dimensions. Correct? Yes. So I look at the unit sphere, and SVD can be used to understand what a matrix, a given matrix A, how it changes vectors from the unit sphere. This will help us understand SVD. And you will get an equation like, you'll get an ellipsoid equation. In case you're running out of patience, the final stop will be an equation of an ellipsoid. And let's get there. The way to get there, before that, so since I'm assuming invertibility, I'll get a, this matrix. This matrix will have, no zeros along the diagonal. Is that clear? No zeros along the diagonal.
Yes, it's clear.
Yeah, that much has to be cleared. And now I take this. If I have to invert this, it goes in the reverse direction, and Q2, the inverse of this is just Q2 and so on, and the inverse of this is just this. And sigma inverse is like you take this matrix and invert each of these entries. And then we'll have just 2 lines to understand SVD. But the geometry is coming soon. So take something from the unit sphere. Take an x from the unit sphere and let y equals whatever A does to that x. Okay, this is just a notation. I'm taking something from the unit sphere and applying this matrix A, which has SVD in this form. And I'll do some algebra, but it will lead to an ellipse equation very soon, ellipsoid equation. So if I take an x from the unit sphere, I know that x transpose x is 1, norm x square equals 1. And I can trivially write x as A inverse A, which is identity times x with a square. And AX in my notation is y. So until here, is this okay? Unfortunately, the moment I start sharing my screen, I can't go back, and since you're also not sharing your screen, I can't really get any feedback about whether people are following or not. So I have to ask this okay now. Is this
Yes, sir.
okay?
Yes, sir. It's okay.
Yeah. Yeah. Thanks.
Yes.
Yes, sir.
So periodically just say okay, whether you're listening or not. Now A inverse has this form. The reason why I wrote A inverse was because I want to write A inverse like this. A inverse is this form. And what is the norm of Q2? Q2 goes off because norm of Q2 is 1 because it's an orthogonal matrix. That's something I'll just leave as homework because running out of time. So take out Q2, I'll get this. Yeah, and the important thing to observe is if I write this Q transpose Y as some other new variable, then this is an equation like this. And the ellipsoid equation is just one step away. What is this norm like? If I expand this, the sigma inverse is like you take this matrix, invert each of them, multiplied by some z's, which are q transpose y, q1 transpose y. And now, what is? Can somebody tell me what this equation will look like? What is this vector? If I multiply this,
Z1 square by sigma 1 plus Z2 square by sigma 2 up till Z square.
yeah, there will be a sigma 1 square because it's the norm square. Now, do you see this boxed equation? What is this?
The ellipse equation.
Yeah.
Ellipsoid equation. as it's called.
Got it. So you got a ellipsoid equation in what variable? So y equals ax and z is q1 transpose y. So I take something from the unit sphere and apply a, and this then q transpose, q1 transpose. Oh god, q1. Yeah. Then if I look at this variable with an x, yeah. Then if I look at this variable, then I get a ellipsoid equation in z. Now just go back to this assumption. Somewhere I wrote sigma 1 greater than sigma 2 greater than sigma d. Okay, got it. Sigma 1 is the largest singular value. If sigma 1 is the largest singular value, what is the principal axis of this ellipsoid?
Sigma 1.
Yeah, it's sigma 1. Got it. Because it's in the previous case, I had a lambda 1 z y1 square plus lambda 2 y2 square. Whereas here I'm getting it in the denominator. So sigma 1 is the one that decides. Okay, so the axis lengths are sigma 1 to sigma d, and the major axis is decided by the largest singular value. This is the largest singular value. Okay. The second thing I want you to notice is if I take something from a unit sphere and if I apply a matrix A to that, left multiply by A, then rotate, then what I get is an ellipsoid equation. Now what is this Q1 doing? It's just rotating. So even if I don't rotate, I will get an ellipsoid equation. Is that clear? This won't change the length. Will Q1 change the length of AX?
No, sir.
So it won't change. So the point I want to make is Q1 transpose will only change the orientation by rotation. So if I take an X from the unit sphere, apply A, I'll still get an ellipsoid. That's the point. So if I take the unit sphere and apply A using SVD, I can argue that it is an ellipsoid with axis length sigma 1 to sigma d and the major axis is sigma 1. That's the geometric interpretation. Okay. Any doubts? I mean, I think this derivation, I'll let you look at this derivation for a while until this. But if you have a doubt, this is the time to ask. Probably this is the first time you're seeing it if it went too fast. The thing to recognize, I mean, if you go back to the earlier positive definite case also, we got the ellipsoid equation in Y, and Y is Q transpose X. And because Q is only rotating, even in X you got an ellipsoid equation. Or ellipse equation. In this case it was just R2. Do you understand the point? This Q is just rotating, so even in X it is an ellipse equation. This is the equation in Y, which is obviously an ellipse equation. And this is the equation in X, again this is an ellipse equation because of Q. With all this hard work and multiplying, you still got an ellipse equation because Q is an orthogonal matrix. If this was not an orthogonal matrix, if it was some other matrix, then you won't get an ellipse equation in X, even if you have an ellipse equation in Y. That's the point I want to make. Anyway, so if you come to SVD, just look at this derivation. The thing to use is if I take something from the unit sphere, I think you can use the same logic there also. If I take something from the unit sphere there also, it's still getting me to an ellipse. Yeah. But here I didn't use the fact that, A is real symmetric. There I'm using it. So positive definite case, the entire, the diagonalization and all of that, use the fact that it is real symmetric. And then you can come up with an ellipse using the eigenvalues of the matrix. Whereas here we didn't use we didn't impose symmetry. So you take any matrix, use the SPD, and you get an ellipse using, the singular values. The lengths are decided by the singular values. So I hope you can contrast these two cases. Yeah.
Sir, in summary, like what exactly will you do for the SPD, like the ellipsoid and the ellipsoid?
No, in summary, what I'm trying to tell you is you take anything from the unit sphere. I don't know how to draw this. Okay, let's draw something. You take anything from the unit sphere. Let's see if it makes a round thing. Then apply A. What you'll get is an ellipsoid whose axis get decided by ellipsoid axis lengths sigma 1 comma sigma 2. Major axis length sigma 1. Got it? So I can justify this interpretation only using SPD. Understood?
It means that like using SPD, I can convert this ellipse into ellipsoid with rotation of the axis.
Yeah, with rotation. So the point I'm trying to make here is I got an equation, ellipsoid equation for which variable? For Q1 transpose times AX, but Q1 transpose is just going to rotate things. So in AX. So whenever I apply A to something from a unit sphere, what I'm getting is an ellipsoid equation, which is not exactly this because this includes rotation. I'll have to cut the rotation. Yeah. Got it?
Yes, sir. But like when that becomes unit factor for the multiplication one, that Q transpose one, so in that case also it does not give the ellipsoid.
No, I didn't understand. What in the
If the multiplied factor like Q1 transpose that becomes unit factor. So in that case also it becomes rotated and gives the ellipsoid.
Because this won't change. I mean, if you take any vector, right? If you take a vector like Ax is vector, what is Q1 going to do? It's not going to change the length.
Length will remain same, yes.
Length will remain same, so it's going to rotate. So take all the Ax's and apply Q1. So if all the Ax's with X coming from unit sphere had the point I'm trying to make is Q is only going to rotate, it's not going to change the shape. Yeah, I hope that part of the geometry, I don't know how to put it in words.
Yes, I got it.
Yeah. So Q is not going to change. Like, so for example, Q is not going to do some stretching of the axis such that you have an ellipsoid, and if I apply orthogonal transformation, then it's going to become a sphere or something. It won't do that. Yeah. Yeah. Okay. Any other questions? I think PCA will require another session. I think we had so much geometry already today. If I cover PCA, it's just too much. Yeah. Probably we can plan a follow-up session at a later point where I'll cover some geometry of PCA. Yeah. But it's entirely tied to SVD. If you look at the class or the lecture notes, in high dimensions to achieve PCA, you are going to use SVD. Anyway, for PCA, I can do some simple interpretations. If people have the patience, I'll just tell you. I'll just ask some questions, some simple questions about PCA. Let's take the 2D plane itself.
Sir, here's a small doubt, sir.
Huh.
Like in the principal axis, no, that major and minor axis. When we are rotating, that takes the form of an ellipsoid. The major and minor axis also get changed, right? It's
Don't get. I mean, they will get rotated, correct, but their length won't change.
Vector length is not changing, but the geometric interpretation for which you
Correct, it will change. Obviously change. I mean, for example, look at this. I will draw an ellipsoid for you. Let me draw an ellipse for you. Okay. And there you are. What happened? Oh God, I don't know how to redo. Shit. Okay. See, if I rotate, the length will remain same, but the axis will change.
Sir, but the previous one you drew a circle, but when we rotated, it became an ellipse. So I just
No, I'm not talking about that. I'm just saying that if you apply orthogonal transformation, you can go from here to.
along z-axis, if I rotating, that will remain same. Like
Sorry, I'm just struggling with this app to draw an ellipse. Okay, thanks. Assume both ellipses are like same length. It's just hard to draw the exact same ellipse. Maybe I should make it bigger, is it? Hopefully bigger. Yeah, so actually I can do this. Delete. Copy. Now rotate. Okay, now it's fine. I can use an orthogonal transformation to go from here to here. So if I draw the axis, obviously something like this, and it becomes like this. Right. But the length will remain same. If this was sigma 1, sigma 2, sorry, the other way, sigma 2 and sigma 1, sigma 2, sigma 1. Okay. So the length will remain same. But the vectors, because of rotation, the vectors will change, the axis will change, but the length will remain same. And the shape will remain same. It will remain an ellipse, it won't become something else. This is not about PCA. Is this point clear?
yes, sir, this is clear, but the previous picture, what you have drew already, that circle and then the ellipse one.
Oh, that is okay, like this.
Could you please go to the previous one?
No, that got deleted. I was trying to undo. I tried to undo something about an ellipse, and that got deleted.
Yeah, here actually, what I understood, the sigma 1 and sigma 2 in the left side and in the right side, it is different. Like, so that's what I just wanted to understand what
No,
happened
this
here.
is an X. Yeah, this is unit circle. Yeah, and take some X. Okay, and apply A. And then you'll end up with an ellipse with some length sigma 1. Got it. So what does a matrix A do to vectors from the unit circle? It makes them an ellipsoid whose lengths are sigma 1 to sigma d. That's all I want to make. That's the point I have been trying to make. And this explanation came entirely because I used SVD also. You understand the point I'm trying to make?
Yes, sir, yes, sir.
Yeah. So the point is I'm taking an X from the unit sphere and I'm applying AX. So I'm looking at AX, but I'm not just looking at AX, which is Y, but I'm looking at Q1 transpose AX. So if I ignore the rotation bit, then I'll still have an equation which is like an ellipse. That's the point. Yeah. Okay. Oh, it was here, is it? Shit, I thought I deleted it. Yeah. Okay. Yeah. Okay. We still have about 8 minutes. If you want that, I mean, I don't know. I think PCA will do it some other time. But okay, I can tell you something quickly about PCA just to see the connection. I'll just ask, okay, I'm not going to do detailed justification because of lack of time. Let's draw the 45-degree line and draw 3 points. Okay, yeah. If I have a data set which is like 0, 0, 1, 0, 1, 1, okay, yeah. This is a data set in R2, right? Clear?
Yes, sir.
Yeah.
Yes, sir.
So I want to find a line, find the best line. If I do PCA, I mean, I'll try to, I think I used M, do PCA with M equals 1. So which is that line that I will get if I want to fit it to a low dimension? Yeah. It is like find the best line using PC.
It will be the same line.
Yeah, it's already on the line. Clear? Now if I were to change this and put a lot of points, okay, and if I still want to find the best line, the question is, where will that line pass through? Can you give me a vector? Can you specify that line using a particular vector? Eigenvector or singular vector? This is the question that will help you answer the. You remember when we do this, we wrote down that covariance matrix and all that, right? Okay, somebody has to tell me the day, not this. Which week is PCA? 7, is it?
Week 7, sir.
So earlier it was in 6th week.
Yeah, no, I will find something. Okay. No, I want to know. Okay, so do this. You remember this matrix, covariance matrix. So, point I want trying to make is, so if I'm just projecting onto, I can't highlight anything here because I'm just opening from Google Drive. Look at this box with U transpose C equals lambda. So which is that line? If I want to project onto one-dimensional thing, then the line will be U1, right? Corresponding. Understand?
Yes, sir.
So the point I'm trying to make is it's just going to be that singular vector corresponding to, yeah. So if you have a bunch of points which are not necessarily on the line but very close to a line, the closest line that will be found by PCA will relate to some singular vector. That's the thing you have to go back and understand. That's where all the geometry will come. Yeah. And I can achieve PCA using SPD. That's the higher dimension bit. Okay, so if you go back to the class notes, you can understand this. Yeah. And also when I'm doing low dimensional projection, I think when I was trying to talk to students also, when I do low dimensional projection, if I take these 3 points, then these 3 points after PCA will remain just as is. So when I talk about a low dimensional projection, it's not like making one of the coordinates 0. So please don't get confused. I've seen many students get confused like this. So I'm clarifying. So these are points in R2, but they lie on a line. These red points lie on a line. It's low dimensional in that sense. You want to find a line which fits the data, and PCA will do that. So you want to find, and the best way to do that is to use singular values and singular vectors. And whatever I derived is like a concrete motivation for it. We can do a little more, but I think PCA we can refrain from discussing today. But there's a connection from PCA to SVD. So, I mean, you go back and find the best line. I think you understand what PCA is doing. Okay.
Sir, are we going to take any class in coming week on PCA?
Well, that I don't know. We'll see. Yeah. I think geometry I covered. I think only PCA has to be covered. But if I start covering extra material, I don't know how this course will pan out. That's my confusion. Like this geometry, whatever I covered, can be seen as like probably you will be able to understand the subject matter better. And I wanted it to be a live session because the recording is not something that I like. Yeah. At least here, if people ask, I'll be able to clarify. Whether if you put me in a studio, then my teaching will be, yeah. I can't say anything on the record on that. Yeah.
Sir, that's the request from our side. If you can have some 1 or 2 classes, live classes like this, so that
Yeah.
the concept can
If PS, ask me for a bunch of topics, then I mean, if I get some topics, then I can cover. Otherwise, it's very difficult. What should I do when the class is not clear?
So it's better we'll figure out some good topics and we'll post it on Discord. So I think Ram may coordinate.
write a mail to the support team so that on those topics you can take classes.
Yeah, so if you're facing difficulty with some topics, you have to be very specific because I don't want to go through the notes again. That's boring for both of us. If there are some specific topics, like for example, SVD, PCA, or something like that, then I can, approach the topic, using in a different direction and still hopefully make you people understand.
Sure, sir.
Yeah, but you can't say it's already like 10 hours of content, so you can't. I mean, don't be expansive in your selection. Just take the most toughest. It's like singular vector. There should be some topic which is like the top eigenvector in your understanding. Just pick the topic that you don't understand at all and ask me. Because if you pick, I want a low dimensional projection of your understanding so that I can only clarify that. That's an academic joke. That's a joke, linear algebra joke. I hope you understood what I was saying. So if your understanding were to be like a linear space, pick that eigenvector which is most troubling for you.
Sure, sir.
Anything else? How many students are taking this course? A lot more, right?
Yes, sir. Approximately, I guess, 1400 or 1500.
Oh, 1400. Here is 1, 2, 3, 4, 5, 6, 6, 3, 7, 18, 19, 20. They cut out 4, 3 years. Yeah, 20.
Yes, and the live session mostly 20-25 people generally.
Yeah. Anyway, I mean, see, the point is that notes is very hard to just pass through directly. Maybe if this session recording they see, they'll be able to understand because it's not like I've written it like a textbook. I explained a lot orally. But hopefully, I think the geometry helps you solve problems better, understand eigenvalues, projections, SVD, singular vectors, ellipse, all of these things better, hopefully. Yeah. Anything else? Are we done? Any doubts, questions on the matters taught?
Sir, how can we connect with you if you have any doubts in the future?
Well, that's very difficult. That's something you'll have to come through TAs. Yeah.
Okay.
You'll have to come through TAs. If there is like a pile of questions, then I can take a session. I mean, otherwise, I won't be able to offer tech support or something. Yeah. The other way to connect with me is to join me as a PhD student. Yeah, but that's too far-fetched. So I think approach the TAs if your questions are not clarified, if some concept is not clear, just list them. I can handle it in a live session. I'm happy to do these live sessions because I think you're a good audience who's interactive and things like that. So I'm fine doing another live session provided there are some topics that you're facing difficulties with and I can clarify.
Sure. Thank you so much.
Okay, Vishal, Ram, whoever is there, are we done? Can we sign off?
Yeah, sure, sir.
Okay, thank you all. Have a nice weekend. Yeah.
Thank you so much, sir.
Thank you very much, sir. Thank you.
Thank you, sir.
Thank you for your time, sir.
Thank you. Vishal sir, are you there?
Yeah, I'm there.
Sir, now we can go with our questions.
Okay, I'll just Ram, are you here? Okay, I'll just ask him to join and then you can ask Ram. Okay?
Okay.
Sir, what doubts? Hello?
Yeah.
Sir, how PC is using SPD? Can you give an example and show this?
1 second, I'll just ask Ram to join.